Good morning. So our last lesson of this half term. So here's your starter, and we've just got 4 reasonably straightforward questions to get us in the mood here. So you've got your 4 questions. So if you'd like to pause your video and do your rearrangements. Okay, here's your answers to the starter. So the answers are in blue. Okay. So what I was trying to get you to spot here are that there are different rearrangements to the same equation. So there's different ways of you getting ready to do an iteration. Right, what we're going to look at today is the limitations of iteration, of fixed point iteration. Now, we can sort of only really go so far with this topic because we haven't done the year 13 differentiation, and the year 13 differentiation and integration is a really big topic that we're hopefully waiting to do when we get back to school. So the first bit of this topic is going to be okay. The second bit, which is where we look at the condition for things not working or things working, really needs us to be able to do any really of the questions. It needs to have done a bit more differentiation than we have done. But I'm going to introduce that rule to you so that it's part of your notes in this topic, and it will make more sense when you've done more differentiation after, when we come back to school. Right, consider the equation x take away e to the x plus 2 equals 0. And you cannot solve this equation algebraically. Can't do it. Well, not without to get an exact value. Well, so what we're going to do is we're going to rearrange it. So I've rearranged it into the form x equals e to the x minus 2. Now, I mean, the reason it's so difficult to solve algebraically is because, you've got these 2 x's here, and it's really difficult to get some form of single value of x. So what we're going to do is we're going to set up an iteration formula from our rearrangement. Now, I've put this in my graph in my graph bit of my graphical calculator. So I've entered y equals x, and I've entered y equals e to the x minus 2. So that was my y1, that was my y2, and I've worked out where they're crossed, and it's approximately 1.15. So I know that there is an answer. So what I'm going to do is I'm going to do this as an iteration. So obviously I can't go straight in with what I know the answer is. So I'm going to try a number very close to it, which is 1.5. So this is my calculator doing the iteration. And obviously you might just do that in run, or you might do that in recur to get your values. Now, especially if you're doing it in recur and you have quite a few values, you will see that you are moving, you're not heading towards 1.15, you are moving away from 1.15. So you can see the iteration is diverging. If you look at it graphically, you can see I have got a staircase diagram, but it's not a staircase diagram going in the right direction. Going in the right direction. So I know that's my solution, which I know because I've used my calculator, my fab calculator, is 1.15. So I've started here just to the right of it. I want to go curve, line, curve, line. It's moving away. So this is not going to give me a solution from iteration, which is obviously a big concern. But I might try this side of the route. So I might try slightly smaller than 1.15. I'm going to try with x1 being 1. So what happens here is it's diverging. It's diverging away again. So here's the route. If I try x equals 1, now here's my calculator iteration, and here's my diagram. And again, it's a staircase, but it is moving away from that route. It may be that, and it looks like, yeah, I might have another route over here that it might be converging towards, but it's certainly not heading to that route there. So it looks like wherever I start, either to the left of my route or to the right of my route, there is no way that this is, using iteration, am I going to converge towards my solution? So we need you to understand what's going on here. Even if, you know, you may never be asked to get it into a form that's correct, but this syllabus needs for you to understand how it goes wrong, or why, you know, what's happening, or that it's gone wrong. So let's go back to that equation. So let's go back to that equation, and maybe it'd been nice if I sort of revealed this a bit more. And what we're going to do is we're going to rearrange this equation in a different way. So if you think back to your starter, you were rearranging them in different ways. So what I'm going to do first of all is I'm going to make e to the x a subject. So I'm going to add that to the other side. And now I'm going to take natural logs of both sides. You know, that's the only way that I can get that x to not be a power or an exponent. So, sorry, birds just hit my window there. So I've got, if I take logs of both sides, the x will come down. And of course, I know that the natural log of e is 1. So there I have a totally different rearrangement of this equation. I'm going to sketch the graphs, so because that can always help me. And also I'm going to set that up as an iteration formula. So again, I'm going to start with the same value that I started in the previous rearrangement, and it got me nowhere. It moved completely away from my route. It diverged. So let's see if I have any better luck with this one. This is my iteration that's gone into my calculator, and you can see that it didn't take me very long, 5 goes, and I've started repeating to 2 decimal places, and it has gone straight to that solution. It's gone straight to my route. It's converged. It's worked. So it wasn't that we couldn't use the equation, and it wasn't that we were taking the wrong values of x. It was just that the rearrangement we did in the first bit didn't work, wasn't working. This is what it looks like graphically. So you can see here, okay, here's my y equals x, and it's obviously a different curve. So you can see that if I start at 1.5, here's my route. I've gone curve line, curve line, curve line. It has converged pretty quickly to my route, my solution. You can see as well, there are 2 routes to this equation. You've got a route here and a route here. Can we get to the other route using iteration? Well, let's have a little look. Let's try x is minus 1.5. So if we try x is minus 1.5, so we've got curve line, sorry, curve, let's have a little look. So here's my numerical iteration. Might be easy to see here. So I've started here with my curve line, and you can see it's gone back up to this route here. And if you put that in your calculator, you'll find that it'll go back up to this route here. And and here you can see if I try x is minus 1.9, and I go to curve line, it just diverges away, and then suddenly error. So in this arrangement, yes, you can see from your iteration, so you've got basically curve line, curve line, curve line, curve line. In fact, I wonder whether that little bit there is a little bit misleading. I don't really know if I like that very much. Right, I think that makes it look better. Curve line, curve line. You can see from your iteration that when you try minus 1.5 and on your calculator, it will zoom back up to this root here. And when you try the other side of that root, it goes off into the abyss because of the nature of your log graph here. So even with this rearrangement, you can't get both solutions. You can't get your iteration to ever work to this solution here. Okay. This is for your notes, okay? Some rearrangements of the equation lead to convergent sequences and others to divergent sequences, whereas this is the same equation, just different rearrangements. A divergent sequence does not find the required root. If an equation has more than one root, different rearrangements may converge to different roots. And we will come back to these terms, convergent and divergent, when we look at sequences and series next half term. Right, quite a big example, quite a tricky example, but let's take our time and have a quick look at it. Part A, show that the equation of x equals 2 cos x has a root between 0 and 2. So instantly we should think sign change rule. So the first thing you're going to do is you're going to rearrange that so that it's in the form f of x equals 0. So I've taken x off both sides and I've rewritten that as 2 cos x minus x equals 0. So you know that it has to be in radians. And always assume radians unless it states otherwise. So you will find f of 0, which is 2, which is positive. You will find f of 2, which is negative 2.83, negative. Make sure you indicate your positive or negative signs. There is a change of sign or sign change rule, so there must be a root between 0 and 2. Done. Let's now go back to B. So let's go back to B. Starting with your first iterate equaling 1, find the next 4 terms in that sequence. So using that iteration sequence and describe the behaviour of this sequence. So you decide, you can be in run in your calculator or you can be in recur and write down the list. So it's totally up to you, but they're asking you, they haven't specified a level of accuracy here. So use your common sense. You can see here. So you've got 1.08 and then it comes down, but then it goes back up, but then it comes down, and you can see that if you were to draw this, it is going to be a bit like a cobweb diagram. It's getting further away. You're not oscillating towards a point, you're oscillating away. So if you could almost sort of think of this as some sort of zigzag, as sort of going like that. You're getting bigger and bigger and bigger, and it's like oscillating away, isn't it? So I don't really want that in my, when we have our notes, but I'll get rid of that. So let's now look at part C. Illustrate the behaviour of the sequence of the cobweb using a cobweb diagram. So what you might want to do here, what you might want to do here is actually have the question in front of you. Here we are. Is you're going to have to do a little sketch. In an exam, what they would probably say is, because you get a printed answer booklet, they would probably have the graphs drawn for you. So what they might do is they might give you the graph of y equals 2 cos x and y equals x. You obviously, to do this, you would have to sketch those graphs. So have a little look here, and so I've drawn the diagram for you. So here we have y equals x, y equals 2 cos x. And if you start at 1, you can see it's spiralling out. It's spiralling out. So you can see that that is indeed a cobweb diagram. Right, it's not worked, has it? So you don't have a convergent sequence here. It's not converging to a root. So you're going to try another version of this. So you're going to rewrite this. You've already done this in the starter. You're going to rewrite it in this format, and then you're going to try your iteration. So already done this. So you take your x equals 2 cos x, and if you think of that as similar to what we did in our starter, so you can, and a good use of your if and only if proof symbols there. So you've then got your iteration sequence, which is going to look like that. Again, you must make sure you are in radians. Either use run or recur and substitute your values in. So again, you were given your starting value. Or no, you weren't. Let's start again with, we'll use x equals 1 here as our starting value from B. I think that makes good sense. So if you use your first iterate as 1, you can see that with some button pressing, you are converging towards a root. So at 3 decimal places, your solution is 1.030. So in this instance, you had your first rearrangement did not lead to a solution or a root from your iteration, but your second one, your one in D, did. Okay, example 2. Describe what happens with the iteration starting at x1. So there's a bunch of questions from the textbook that I'm going to ask you to do, and they're all a bit like this. So the first couple don't have any labels there, and so all you will do, if they don't have any A, B or C, you will say, oh, converges to the root or diverges away from the root as a cobweb or a staircase or whatever. And if they do have like A, B or C, then obviously it's gonna head to one of the roots. So starting at x1, describe what happens. So I'm going to remember that I go curve, line, and I'm going to use green. So here I go. So curve, line, curve, whoa, not like that, I'm not going to go. So curve, line. You see, I'm not doing particularly well with this. It seemed like such a good idea. And I'll go back to my line here, and I'll get rid of that random little line that I had a moment ago, and I don't even know whether it's green. Now I've gone into black. So I'm afraid I've done a bit of a multicoloured staircase there. So what I've got is, with that x1, it has converged towards root B, and therefore your notes, I've got a better version of it. So there's your staircase converging to B. So I would now, I think, like to get rid of that. So, right, could you do these questions? So you've got questions. So they're from the textbook, so it would be good to print them out. So you've got 6 questions here. So again, print them out from the PDF. So they're your first questions. So if you pause the video or print them out, have a go at those. Here are the answers. Right, this next bit is a bit harder, and we can't really go into it in very great depth because it requires us to be able to differentiate more functions than we currently can, but we will do after we've done our further differentiation topics. Can we make a rule about whether an iteration will converge or not? So what you've seen is us with different versions of the same equation, and some of them have converged and some of them haven't. So let's have a look. Here, this converges. You can see it converges to the root. Here, it's diverging. It's not working. So what do we notice? Well, what we notice is that at the root, the gradient here of this function isn't that steep. But here, the gradient of this function, the blue function g of x, is much steeper. So this is what we tend to say. It's to do with the gradient. The gradient for the convergent bit, the gradient of your function g of x at the root is smaller than the gradient of y equals x. And here, the gradient of your function is bigger or steeper than the gradient of y equals x. That would be our way of looking at it. And of course, gradient is us differentiating it. And if you think about some of the functions we've been dealing with, we don't yet know how to differentiate those, but we will. It is hard to see in a cobweb diagram. Here's one that's converging. And this is because it's got a negative gradient, and it's hard to compare a negative gradient with a positive gradient. Now here, again, you can see that this gradient is less steep than this gradient. So we just need a way of summarizing that. Now we use the notation of dash to show that we've differentiated the function, and we are going to summarize it like this. So we'd like you to put that in your notes in this topic, but we will do more questions using it when we've done more differentiation. So fixed point iteration written in this form. It converges if the size of the gradient, remember those modular symbols mean size, so the size of the gradient is less than 1. So that means you have a small gradient, and it can be a small gradient, a small positive gradient, and a small negative gradient. So around the root, okay, it doesn't have to be specifically the root, but around the root, you need a small positive gradient or a small negative gradient. Of course, small is a subjective term. That's why we have less than 1. And also, you need your starting value sufficiently close to the root. Again, sufficiently close. That's worthy of discussion. It will diverge if your gradient is larger than, the size of your gradient is larger than 1. So obviously, if you've got a steeper gradient, whether it be positive or negative, it will diverge from the root. Now, you are expected to know that. But from the exam questions we've seen, there's not that much that they've asked you about it. So I have tried to sort of go, you've had to look quite deeply to try and find a question. Right, let's have a look, and this is the question in action. It's a bit harder, so we will do more of this when we come back. Show that the equation x equals 2 minus e to the half x has a root between -4 and -3, and another root between 1 and 2. Absolutely great. So you would rearrange this to get it in the form f of x equals 0, and that's not right.